Example 3.4 kind of continues with example 3.3. In example 3.3, we had $1,000 that we were going to deposit in a bank account today. We were going to let it earn interest, 10% interest over 30 years, and we wanted to know how much we would have in our bank account at the end of that 30 years. Well, example 3.4 just kind of flips that on its head. It looks at it from the other direction. And here's the setup. So suppose you wanted to have $17,449.40 saved 30 years from today to purchase a boat after you retire. Hey, it's good to have goals, right? If your bank pays 10% interest per year, how much would you need to deposit today in order to have $17,449.40 in 30 years? So if we look at our timeline, it looks just like the other one, except now at time period 0, we've got a question mark. Our present value is unknown, but we know how much we want to have saved in 30 years. We want that $17,449.40. So what will we have to deposit today in order for it to accumulate interest 10% over 30 years and grow to $17,000 and change? Well, in example 3.3, we compounded, right? We started with the present value of 1,000, and we multiplied it times our interest rate factor raised to the 30 to earn compound interest over that 30 years. Well, now we're looking at it from the other direction. We know the future value of $17,449.40. We want to discount it back to present value. So instead of growing that amount, we want to shrink it with our interest rate factor down to whatever it would be at time period 0. Now, when we had the interest rate factor 1 plus r in example 3.3, when we flip that thing on its head, when we have 1 over 1 plus r, that's now the discount factor, and the units flip as well on it. But that's another conversation. It's in the text ahead of this, and I encourage you to go back and read it if you haven't, because it's neat the way it works out. So just to apply this here, all we're going to do is take this equation, and let's talk about real quick where that equation comes from. We have already used the future value, present value relationship in this format, where future value is equal to present value times our interest rate factor of 1 plus r raised to the n, the number of compounding periods that we have. Well, this is great if we're given a present value and the interest rate and the number of compounding periods like we were in example 3.3. In this problem, we're given the future value, the interest rate, and the number of periods, and we need to solve for the present value. Well, let's just rearrange this equation so that the present value is on the left-hand side and all the other stuff is on the right-hand side. And the way we're going to do that is we're going to start off by dividing both sides by 1 plus r to the n. So that over here on the right-hand side, I've got 1 plus r to the n divided by 1 plus r to the n. Well, that's 1. Those guys drop out. And on the left-hand side, I've got future value over 1 plus r to the n is equal to present value. Okay? Now I've got present value by itself over here. Now we usually like to have the thing that we're solving for on the left-hand side, so I'll just rewrite that as present value equals future value over 1 plus r to the n. Right? And now we've taken the same relationship that we had before, and we've just converted it to where present value is on the left-hand side. But it's exactly the same relationship. We're just looking at it from a different direction. Now, you'll notice on the formula sheet, I have it, or on the formulas in the chapter, I have it written as future value times 1 over 1 plus r to the n. Now, these two equations are exactly the same. They're the same thing, just written in different ways. I have it written this way on the formula sheet so that we can see the discount factor at work here. We can know that we're taking the future value, we're multiplying it by something smaller than 1, and so the present value must be smaller than the future value we're starting with. And compare that to the future value present value relationship where we're multiplying by the interest factor, which is greater than 1. So when we start with a present value and we're calculating a future value, then the future value must always be larger than the present value. And we can kind of see that at work in the formula for future value. And then when we rearrange it for present value, we can see the same relationship at work, just in the opposite direction. When we start with a future value and we're going to convert that to a present value, or we're going to discount it back to present value, then our number should always be shrinking, right? Our present value should be smaller than our future value. And we can kind of see that at work with the way these formulas are written, and that's why they're written that way. But these two are exactly the same. Okay, now let's look at the actual problem. So we want to have $17,449.40 saved 30 years from today. So what we're going to do is just plug in the $17,449.40 into our future value in that formula. We'll plug in our 10% for our interest rate, and then our N is 30. Right, and we can just walk through and solve that. We can plug it into our calculator, and of course, we already know we're going to end up with $1,000 at the end of that. So let's say, probably mostly gentlemen, although I'm sure some ladies as well, if you want a boat that cost almost $18,000 30 years from today, at some point, just when you retire, so you can go fishing, just drop $1,000 in your bank account and let it grow over 30 years. And of course, you're not going to earn 10% interest. You're probably going to have to throw some more cash at it, but let that interest work for you while you're saving for stuff. It's an incredibly powerful force. Okay, the other thing I wanted to look at with this one is the financial calculator solution. So let me skip to the appendix for this one, and so we can look at the calculator inputs, and then I'll pull up the calculator as well so we can see it going in. If I can get this out of the way. Well, okay, going to be there for now. All right, so this is the same problem. We're going to, of course, the previous problem, I've still got example 3.3 in here because it's the last one I worked. Remember, these time value money keys are memory keys, and so whatever you worked is still in there, even if you shut the calculator off and turn it back on. So I'm going to start by clearing out the time value money register by hitting second and clear TVM, second and clear TVM. We'll record zeros on all the time value money keys. All right, and then I'm going to work left to right. I do that as a matter of habit just so I won't forget to enter a number on one of the keys. By doing it randomly, I'm likely to forget something. That's just the way my brain works. You develop a habit that works for you to help you keep track of everything. N is 30, so I'm going to type in 30 and press the N key to store it. The interest rate is 10, and that I over Y key that takes the interest rate is expecting a percentage. It knows that should be a percentage. So instead of converting it to 0.1 as a decimal, which we have to do in the formulas, we type in actually 10 for 10%, and then press the I over Y key to store it. Present value is what I'm solving for, so I'm going to skip over it on this one. Payment is 0. It's 0 in all of the Chapter 3 problems because payment it would be a reoccurring cash flow that happens over and over again, and we don't have any of those. We'll start having them in Chapter 4. Future value is $17,449.40. That's what we want to have saved. And now it's entered as a negative here, and this one it doesn't really matter if you do it as a positive or negative. In this case, it's looking at it from the perspective of the bank account. And so the $17,449.40 is going to be a cash outflow from the perspective of the bank account because we're going to take it out and pay for the boat with it or whatever we're going to do. So I'm going to record that guy as a negative, press the future value key, and now I can solve for present value by hitting compute PV, and we get something really close to 1,000. Of course, we've got a tiny little bit of a rounding error there, but it's of course going to round to 1,000 there. Now, I didn't do this in example 3.3, but let me do it here. The signs on this one, if I were to instead record a positive value for future value, so a positive $17,449.40, now I'm just looking at it from the perspective of my pocket. So I'm going to take that cash out of my bank account and put it in my pocket to then go pay for something else with it. But just in terms of the bank account, it's coming in my pocket. And then I were to compute present value with it, I'm going to get the exact same numerical value. It's just going to have a different sign because I've adopted a different perspective. And those signs are just tracking the relative directions of the cash flows, and that's all. It's not saying anything about the value of the cash flows.